Okay, let's do some quick examples here. Let's start with XeF4. So since Xe is my odd one out, I'm going to place it in the center. I'm just going to kind of spread out my fluorine atoms around that center xenon atom. All right, I'm going to give them the right number of valence electrons and kind of line it up so that they're ready to covalent bond. Each fluorine should have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Since they're in column 17, we call that the halogens group. They should start with 7 valence electrons each. 4, 5, 6, 7. And xenon should start with 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Now, in a lot of these problems, you're going to end up with compounds that do not have 8 valence electrons. They have more or less. Do not let that worry you. All our column 17 guys, like fluorine, bromine, chlorine, that are surrounding atoms, we're just going to kind of give them each one bond and make sure that they're kind of prioritized over whatever our center atom is doing. And that's a good kind of general rule. Typically, the atom in the center is making more compromises than the surrounding on the outside. So let's make our bonds. There we go. Okay, so each fluorine gets to 8 valence electrons, and our xenon has, well, some extras. It's got 2 lone pairs of electrons here. It's got a pair there, it's got a pair there. So our AX code for this would be a different color. Let's do, I guess we'll do pink, I guess. So we got our center atom, A. We've got our 4 bonded atoms, which is X4. We've got 2 lone pairs of electrons, E2. So if you go and look that up on the VSEPR chart, the code AX4E2 has to do with an electron geometry of octahedral, because you've got 6 electron domains, octahedral. Okay, and out of those we have 4 bonded atoms. That leaves us with square planar. This is a square planar molecule. Okay, let's try another. BrCl5. Okay, this is going to be kind of weird again, but Br is the odd one out, so I'm going to put it in the middle and just kind of surround it with chlorine, 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 and chlorine. All right, each chlorine is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons because they are all in column 17. And again, we're going to prioritize the happiness and stability, the octet rule, for our surrounding atoms, in this case the chlorine, rather than the center atom, which in this case is the bromine. Bromine also has 7 valence electrons, so 1, 2, kind of line these up, 3, 4, 5, 6, 7. Make our bonds. Share a pair, share a pair. Oops. Covalent bonds. All right, so each chlorine should now be up to an octet. Our bromine has more than an octet, but we're going to be okay with that. We have 1 lone pair of electrons left on bromine. Okay, so we have a total of 6 electron domains again. So our electron geometry is also going to be octahedral for this one. Octahedral. Okay, and our molecular geometry is going to be, let's see, 5 of these are bonded atoms, so it's going to be a square pyramid. Square pyramid. And again, you can look that up with its AX code. We have a central atom A, we've got 5 bonded atoms, so X5, and then an E1 for 1 lone pair of electrons, or it might just be AX5E on your VSEPR chart. Okay, that's how we can get this octahedral and square pyramid stuff. I'm not, you don't just need to like know all these. The VSEPR chart will always be there for you if you need it. You don't need to memorize those. That's a lot of information. Don't waste your brain space on memorizing the VSEPR stuff. Okay. Now the other thing we need to do here is figure out the difference in electronegativities between bromine and chlorine. So we can figure out whether this bond between bromine and chlorine right here is polar or nonpolar. So let's go check this out. So bromine has an electronegativity of 3.0, and chlorine has an electronegativity of 3.2. So if I find the difference between those, 3.2 minus 3.0 leaves me with 0.2. Okay, well, where does that land me on my chart up here? That sets me somewhere in here. Okay, so this is a nonpolar covalent bond. It's fairly well shared across the bond. It's pretty even. Okay, so my electronegativity difference was 0.2. If you subtracted the other way and got a negative number, just wipe the negative off and leave it positive, kind of absolute value it. Okay, the BrCl bond is non-polar. Okay, so chlorine might be pulling the electrons a little bit more towards it compared to the bromine, but not enough to really polarize the bond, not enough to really make it super lopsided. So we call it non-polar. Okay, let's look at another example. Skip down to SF6. All right, got my S as my center because it's the odd one out. I'm going to surround it with all these fluorine atoms. Go. All right, each fluorine gets 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And again, we're going to prioritize these guys and their happiness on the outside rather than the sulfur. The sulfur has 6 valence electrons to start with. It's in column 16. So boom, boom, boom. Just going to kind of line them up so I can bond with all of these. And then let's make covalent bonds to share these electrons. There we go. So again, our sulfur is going to have way too many valence electrons. It's up to like 12. But each fluorine is up to an octet. So we've made most of the molecule pretty happy. Let's do our electronegativity difference. Well, actually, here, let's do the electron and molecular geometry first while we're here. So let's see. We've got a central atom, A. We've got 6 surrounding atoms. So X6, and we have no lone pairs of electrons on sulfur. Again, we only care about what's happening to sulfur for the AX code, so E0. All right. You can also see this as just AX6 on your VSEPR chart. Same thing. AX6E0, or just AX6, corresponds to an electron geometry of octahedral. Again, because we have 6 electron domains. Okay, but since all of those are bonded atoms, this is also going to be an octahedral molecular geometry or molecular shape. Octahedral, octahedral. Okay, now let's do the electronegativity difference of sulfur and fluorine to figure out how polar or nonpolar this bond is. Okay, so let's go down here. Here's sulfur at 2.6, fluorine's at 4.0. So if I subtract these out, 4.0 minus 2.6, I always do the biggest one on top just so I don't end up with a negative. Let's see, I gotta carry the 1. So that comes out to be 4. That's a 1. So our difference in electronegativity is going to be about a 1.4 in favor of the fluorine. So the fluorine has a higher electronegativity, pointing towards it. And 1.4 is enough to land us in here, okay, as a polar covalent bond. So in this case, our electrons are not very fairly shared. Okay, fluorine is pulling them significantly more towards them, and it'll happen in each of these cases. Okay, so we end up with polar bonds here. So each of these fluorines is going to be kind of hogging the electrons. So our electronegativity difference was 1.4. We just subtracted them out, and that makes this a polar bond. All right. Let's see. Let's do another example. I think these might be, oh, these are the last three. Okay, so we're going to do SiS2 first. Okay, so Si is silicon. It's the odd one out. We're putting it in the middle. Putting my two S's on the outside. Each sulfur has 6 valence electrons. 1, 2, 3, 4, 5, 6. Oh, I probably should align some of those up better, so I can make my bonds. 1, 2, 3, 4, 5, 6. My silicon has 4 valence electrons, so line those up. 1, 2, 3, 4. All right, make my bonds. So my sulfurs have gone from 7 valence electrons, from 6 to 7 valence electrons. My silicon has gone from 4 to 5, 6. So they're both not quite there. Each sulfur needs to make one more bond to get ownership over one more valence electron, and our silicon needs to make 2 more bonds. So I think we have some common interest here. If I make a double bond from this silicon to this sulfur and this silicon to this sulfur, that's going to leave me with each sulfur with 8 valence electrons and my silicon with 8 valence electrons. So I'm going to rearrange these electrons, put kind of lined up here. That it kind of looks like the dot on the I is an electron. There we go. There we go. Okay, so there's my double bond on each of these, again, to prioritize making the outer sulfur atoms happy. But in this case, silicon also ends up happy as well, so that's nice. Okay, so an SiS2 molecule is what? Well, let's see. Let's start with the electron and molecular geometries. My AX code here is going to be A for my central atom. I've got 2 atoms bonded to it, so an AX2. And then I don't have any lone pairs of electrons left on silicon, so that's going to be E0. Okay, or just be left out as AX2. If we go and look this up, it's got an electron geometry of linear with its 2 electron domains. And since both of those electron domains are bonded atoms in this case, it's also got a linear molecular geometry. Okay, now we've got to face this kind of new problem. Is the molecule as a whole polar or nonpolar? So in this case, we're looking at how the electrons are shared symmetrically across the whole thing, across the whole shebang. So bond polarity is not going to help us here. You can have polar molecules that have nonpolar bonds, and you can have nonpolar molecules that have polar bonds. Okay, so to figure out whether our molecule overall is polar, again, we're looking for at least one of 2 things, or maybe both. One is lone pairs on center atom, and 2 is different surrounding elements. Surrounding elements. Okay, in this case, I've got no lone pairs on silicon, so that's leaning towards nonpolar. Okay, and I have the same element kind of bonded in both cases of these atoms, so it's going to pull the electron cloud the same way, whether it's this sulfur or this sulfur. So both these cases that could make the molecule polar are not happening this time. Okay, so in this case, this is a nonpolar molecule. Let's try the next one. Let's do Ni3. N's my odd one out, so I put it in the middle. We'll spread out our iodine, iodine, iodine. Each of these iodines should start with 7 valence electrons because they're in column 17. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then my nitrogen is in column 15. So I'm going to kind of line up 1, 2, 3 of these electrons, and then it's going to have an extra 4, 5. There we go. Let's make our bonds. Covalent bond there, share a pair of electrons. There we go. All right, so now each iodine should be up to 8 valence electrons, which is great. our nitrogen still has one lone pair of electrons that's not being used for bonding, which is going to affect our AX code. So our AX code is going to be A for our central atom. 3 bonded atoms makes X3, and then one lone pair of electrons makes E1. Okay, or you might just find this on the VSEPR chart as AX3E. Okay, so if we go and look this up on the VSEPR chart, our electron geometry, we have 4 electron domains. So this is going to be a tetrahedral. Oops, tetrahedral electron geometry. And our molecular geometry, okay, cuts away one of those bonded atoms and replaces it with a lone pair of electrons. So that is going to be a trigonal pyramid. Or trigonal pyramidal. Okay. Now to figure out whether this is polar or nonpolar. Again, we're looking at molecular polarity in this case, not bond polarity. So doing the electronegativity difference is not going to help us here. What is going to help us is looking if we have lone pairs on the center atom, or we have different surrounding atoms. Okay. In this case, all our surrounding atoms are iodine, so that's okay. But we do have a lone pair of electrons here. So what that means is we're going to have a spot on the molecule where we don't have our electron cloud kind of stretched the same way. It's not going to be shared out in the same way. It's going to have kind of a bald spot. Okay, so therefore the electron cloud is going to be sort of lopsided. In terms of 3D shape, our trigonal pyramid looks something like this. We've got an iodine off to the side, you've got an iodine coming out at you, and then you've got an iodine kind of going out into the background there. Okay, so your lone pair of electrons here, okay, is making it a little bit lopsided. We've got your electron cloud being kind of shared to your iodine and to your iodine and to your iodine, and those are all pretty neat and symmetrical, and then you've just got your electron pair here that's just kind of sitting awkward and weird, not bonded to anything else. So this makes a lopsided molecule, which means our charge and our electrons are not going to be distributed nice and symmetrically and evenly across the molecule. So this is a polar molecule, okay, thanks to that lone pair on the central atom. We're going to do one more example here. CH2Cl2. All right, well, I'm going to put carbon in the center. It's my C. I'm going to put my H's and Cl's just out around the outside. Doesn't really matter how I arrange them, but I'm going to put them like H, H, Cl, Cl, like that. All right, my hydrogens are in column 1. They each just start with 1 valence electron. Chlorine is in the 17th column, so they start with 7. 1, 2, 3, 4, 5, 6, 7. And carbon is in column 14, so it starts with 1, 2, 3, 4 valence electrons. So I'm just going to kind of line those up to make sure they're ready to bond. All right, let's make our outer atoms happy. The hydrogens have 2 valence electrons, which is A-OK. We got a duet there. Each chlorine gets to an octet, and our carbon also gets to an octet, so that looks nice and good. Okay, we have in this case a central atom, 4 bonded atoms, AX4, okay, and then no lone pairs on the central carbon. So you could say this is E0, or you could just say AX4 and leave the E0 out. Okay, finding that on our VSEPR chart, our electron geometry is tetrahedral. And our molecular geometry is also tetrahedral. Molecular geometry is tetrahedral. Okay. Now, is the molecule polar or not? Well, in this case, we don't have any lone pairs of electrons on the center atom. Okay, so there's nothing kind of left to leave a bald spot in our electron cloud around the molecule. But we do have different elements bonded to the center. Now, we don't need to go and look up the specific differences in electronegativity, but this is going to end up making a lopsided electron cloud because they're going to pull on the electron cloud differently. Hydrogen and chlorine are going to have a different electronegativity, or at least they're very likely to. There are a few elements that have a very similar or the same electronegativity, but in this case, this is not. We can go and double check if we want. Hydrogen has a 2.2, and let's see, Cl has a 3.2. So we still have an electronegativity difference of like 1. Okay. Now we don't need to calculate that, but it does help to know that these have different electronegativities than each other. Okay. Let's see. Carbon has a 2.6. So carbon is more of an electron hog than hydrogen is. Oops. So if we were to kind of look at where our electrons are being pulled to, oh no. Hydrogen is going to be kind of willing to let its electron cloud be pulled towards carbon, but chlorine is going to pull carbon's electron cloud towards it. So overall, we end up with this kind of net pull of the electron cloud towards our chlorines and away from our hydrogens. Okay, this makes our molecule lopsided and therefore polar. If we were to kind of sketch out our electron cloud around this, it might be something like this, kind of skinny and sparse around our, around our hydrogen atoms, and then we've got all this electron cloud area around our chlorine atoms. It's kind of like a sad-looking butterfly. Okay, so in short, we have different elements bonded to the center atom. That's going to cause lopsidedness in the electron cloud because they're going to pull on the electron cloud differently. Okay, so this is going to be a polar molecule. But the longer answer is, we can see that the electrons are being pulled towards the carbon and then towards the chlorine. They're going to end up lopsided, where our electrons are not going to be fairly shared between our hydrogens kind of on one side and the chlorines on the other. We're going to end up with an electron cloud that's kind of wonky, kind of misshapen. And that is what makes it polar. Okay, so the rest of these examples kind of fall in the same suit as that. One more helpful tip: you are not going to end up with the same molecular and electron geometry combination on any of these. In other words, you're going to have a different AX code for each one of these. So if you end up with two molecules that have the same AX code, double check your work and make sure you're prioritizing the happiness of the surrounding atoms over the happiness of the center atom.